Hey everybody, it's Mrs. Dinkelman. This is a section Unit 7 called Trig Substitution. This is not on the AP exam, but it used to be. I'm going to change that to trigonometric. Okay, perfect. There we go. This isn't a Calc 2 class, so the reason I want you to be able to do this is if you go into a Calc 3 class, I want you to know that this exists and that you can do it, and the professor there is probably going to assume that you already know it, so I want to make sure that we cover it. So you're going to see expressions that are of this form, so something like 9 minus x squared or 9 plus x squared minus 9. Hopefully they're perfect squares, but they don't technically have to be. We're actually going to substitute in a trig equation or trig expression, which maybe sounds a little crazy, but using these identities is going to help us to simplify them a little bit. It's a good time for me to talk about this reference triangle, and you'll see me make it in this first example. And I usually wait until the last minute, but just know that we need to write it at some point. We'll have to look at what we substituted at the beginning, and that will help us in step 4 to change back to x's, at least in an appropriate way. Substitute into your integral, so don't forget about, we also have to replace the dx at the end to make sure it's a d theta. We'll integrate, and then again, last step is to change back to x's, just like we did in u substitution. Okay, so for example 1 here, we have x squared minus 1 is kind of the main component here. I know we also have an x here, but it looks like it's this last form. And since it's x squared minus 1 squared, our a value there is just a 1. So let's go ahead and make that substitution. So x, I guess I better have this ready. So x equals 1 secant theta, so I'm just going to call it secant theta. Again, don't forget about the derivative. We have to replace the dx as well. So secant theta, tangent theta, d theta. So let's start to replace the pieces in here. So we're going to have the square root of secant squared, because we have x squared there, minus 1. And then we have another secant down here just because it happens to be hanging out there. And then we have a secant theta, tangent theta, d theta. So we can see here already that the secant thetas cancel. Now what is supposed to happen in all of these, and many of them are roots, which is really nice, but not all of them, is we see that this secant squared minus 1 is actually tangent squared, and then it's under the root. So I'm going to kind of sneak up here for just a second. So what I really have here is the square root of tangent squared theta, which is really tangent. So let's rewrite what we have here after simplifying a little bit. So we're going to have a tangent from here, and we have a tangent there, and then a d theta. So sometimes now we have to reach back to some of the other methods that we have for finding the antiderivative. I don't really know what the antiderivative of tangent squared is off the top of my head, but if I use that trig identity again, which seems like I already used it, but I'm going to use that one that's there, is tangent is secant squared theta minus 1. And that helps because we know the antiderivative of secant squared, which is tangent theta, and then that's just theta plus c. So now back to step 4, we need to figure out how to turn this back into x's. So there's a couple things we need to do. So I'm going to start with trying to figure out what theta is. So I'm going to come over here and look. If I want to isolate theta, I have to do secant inverse on both sides. So I'm going to claim that secant inverse of x is equal to theta. So let's see if we can get that going. So there's going to be something here, and then minus secant inverse of x. Okay, to figure out tangent of theta, I could sort of do the same thing. I could say, oh, well, that's tangent of secant inverse of x. Well, most of us don't really know what that looks like or how that's going to shake out. So there's really a better way to talk about what that's going to be. So I'm going to think of this back to my original substitution as x over 1 is equal to secant theta, and this is where the reference triangle comes into play. So draw yourself a triangle. Right should be a right triangle. I know mine's pretty terrible. And there's theta. So secant, remember, let's think about cosine first. So cosine is adjacent over hypotenuse. So this is going to be hypotenuse over adjacent. And then we really want to find this other side. And the way we would do that is Pythagorean theorem. So that's going to be the square root of the hypotenuse squared minus the leg squared. So that's just a 1. And this should look really familiar. That third side you find is almost always hiding within our integral. So we can see that x squared minus 1 right there. So that's kind of a good indication that you have the right thing. So now, based on this triangle that has that angle theta, tangent is opposite over adjacent. So that would be the x squared, the square root of x squared minus 1 over 1. So that is what is going to go here. So square root of x squared minus 1 over 1, but I'm not going to put that there. So a lot of steps here. You might understand why they probably took it off the AP exam, just because it takes a lot of time. Okay, example 2 there, 4 minus x squared. So if we look back up at our table, it looks like we're going to do this one where x equals 4, not 4, but 2 sine theta in this case, because 4 would be 2 squared. And you're going to see why we want that in this case here. So we're going to go x equals 2 sine theta, and then derivative again, just so we have that. So 2 cosine theta d theta. Okay, so now my integral is the square root of 4 minus, when I square x here, I'm going to get 4 sine squared theta, and then the dx becomes 2 cosine theta d theta. So you can see now why we chose 2, so that when we square it, these are going to match up and I can actually factor it out. So without doing too much writing, I'm going to try to see if I can simplify what's going on inside this root. So if I factor out a 4, I'll have a 1 minus sine squared theta. And then remember, 1 minus sine squared is cosine squared. So that's what I really have inside this root. So I probably should put a root there every time so we see. So now if I rewrite this integral, I'm going to do a couple things. Square root of 4 is a 2. There's already a 2 over here with the cosine. So I'm going to bring that 4 out here. Square root of cosine squared is cosine. And then I have this other cosine. I probably could have just written that as squared as well, but I want to make sure everybody saw that. All right, so what I'm really trying to do is find the integral of cosine squared. So again, back to last unit, if I have cosine squared, I'm going to have to use the half angle identity. So that's 1/2 times 1 plus cosine 2 theta. So let's see, that's going to be 2 times antiderivative of 1 is going to be theta. Antiderivative of cosine 2 theta is sine 2 theta divided by the derivative of the inside, which is 2 plus c. So again, we have to go back to x's. So let's do a couple of things, and I know I'm going to have to do this reference triangle as well. So first of all, I'm going to write x over 2 is sine theta. So if I want theta, I want to isolate theta, I'm going to have to do sine inverse. Okay, so that'll give me this first part. I'm just going to go ahead and distribute this as I'm talking. So 2 times theta is 2 sine inverse of x over 2. The unfortunate thing about this is it's sine of 2 theta, and if I draw my reference triangle, which I am going to need, so I'm going to go ahead and draw it, that's theta, not 2 theta, so that makes a difference. So sine of theta is x over 2. Remember, this is opposite over hypotenuse. Thinking of SOHCAHTOA. Again, if I want to find this, I have to do Pythagorean theorem. So the square root of the hypotenuse squared minus the leg squared. Again, that should look familiar. That should be in our original problem. So I'm just going to scroll here for a second and look at last section. And I just want to remind you about this last trig identity that I had you memorize or kind of put on here. And this is the reason, is because when we get to trig substitution, we often see this. So sine of 2x is the same as 2 sine x cosine x. So let's go ahead and go back and think about how that's going to help us here. Okay, a little bit far here. Okay, so in my mind, what's happening here is this 2 and this 2 are going to cancel and it decides to write. And sine of 2 theta that I'm trying to look for here, that's really 2 sine theta cosine theta. So I'm going to come to my reference triangle and I'm going to say, okay, well, that's 2 times sine of theta. I actually already have. I didn't have to look at the triangle for that. That's x over 2. So you can see I already have some simplifying I could do. Cosine is going to be adjacent over hypotenuse, so the square root part over the 2. So square root of 4 minus x squared over 2, and then plus c. So clearly there's some simplifying I can do in there, but that's how we use that reference triangle. And sometimes we have to use that identity that I had in that previous unit or section. Okay, really quick wrap up just to think about why we don't use x equals a cosine as a substitute? We technically could, but think about why we might not want to, and then you can get started on the assignment.